so let's continue on. Okay, so next we're going to discuss a concept which is known as Llama Perception. All right, so we're going to talk about when the proton is spinning. So the proton is spinning on its own axis like a tiny little planet. The angular momentum, spin angular momentum points along, if you imagine the proton is spinning around an axis, the spin angular momentum points in that direction, along the direction of the axis. So when an external magnetic field is applied, then a certain phenomenon takes place. So the proton spins on its own axis. The proton also precesses. So you can see a gyroscope precessing on the left-hand side. Precession is the motion that you see here. So this gyroscope is like a spinning top. It's spinning like this, but the top of the gyroscope is also turning along the point of a cone. So precession causes the magnetic dipole moment of the proton to travel along the surface of a cone. The frequency of precession tells us how many precessions happen in a second. So this happens when we apply a magnetic field to the proton. It starts to precess. It starts to move in this way, where it's not just spinning on its own axis, it's also going like how this gyroscope is going in the GIF on the left. And the frequency with which it precesses, that is the number of precessions that happen in a second, is related to the magnetic field that's applied, and it's called the Llama frequency. So this is a pretty important equation that we need to be looking at. So now why this is important is because the RF frequency needed to flip the spins is the same as the Llama frequency. The reason for this comes from quantum mechanics, but why this is important for us to know is because we need to know what radio frequency to apply in order to flip the spins, because it's when we flip the spins and we flip the spins repeatedly that they gain energy, and then they release that energy in a process called relaxation, and that relaxation is what we measure. So we need to be able to flip the spins. The frequency at which they precess is equal to the frequency needed to flip the spins. That's the importance of the Llama frequency. Let's discuss the magnetization. So magnetization expresses the total effect of the alignment of the proton spins. So you can see in the image on the left-hand side, there's 1, 2, 3, 4, 5, 6, 6 pink ones and 4 blue ones. So 6 minus 4, 2 is the total effect of the alignment of the proton spins. That's the magnetization. It's the measure of the net magnetic dipole moment per unit volume. Magnetization is a property of the tissue, depends on how the protons are packed in the tissue itself, etc. Magnetization is directly proportional to the nuclear magnetic resonance signal strength. And I'll tell you why we're discussing magnetization in just a second. So the NMR signal strength depends on B0 and the Llama frequency, which also depends on B0. So signal strength is directly proportional to B0 squared. What this means is, if we want a really strong MRI signal, we need to increase the magnetic field. So it was to say all that I introduced the concept of magnetization. So a note here, we were discussing why, we were talking about protons only and not about electrons. So electrons can behave as magnets too, but electron signals that they emit lie in a different frequency. So they don't affect the MR signal. They won't be picked up by the radio frequency transmitters. So electron signals don't appear at all when we're talking about this. Okay, so what happens is we apply a magnetic field. The protons all align in one direction, some align in the opposite direction. We apply an RF oscillation, which makes the protons flip up and down in their spins. There's a net, increase in energy of the protons. The RF oscillation is stopped. then the RF oscillation has a frequency equal to the Llama frequency, which is the frequency at which the protons are processing. The RF oscillation is stopped. The protons have a certain amount of energy still left in them. They emit that energy as a signal in a process called relaxation. We measure that signal, and that signal is going to give us a picture of the patient's body, and we'll see how in just a second. But that's what we've discussed up until now. Let's keep going. So now we're going to introduce, so we discussed magnetization. Magnetization is the total effect of the proton spins. So we're not talking about individual protons anymore. We're talking about all the protons which are in a certain volume. So longitudinal magnetization is the amount of magnetization in the same direction as B naught. So imagine that all the protons are aligned in a certain direction. All of their magnetic dipole moments are aligned in a certain direction. Suppose that direction is this much. So you might remember from your classes on vectors that a vector can be split into two components which are perpendicular to each other. So similarly, the magnetization of the total magnetization, that is we're discussing all the protons together at this point. The total magnetization has a direction, and the longitudinal magnetization is the amount of magnetization in the same direction as B naught. So what's happening here? You've got protons with spins like this, you've got protons with spins like this, you've got a lot of different protons like that. You add all of those spins together. That gives you the total magnetization. Now you're going to split that magnetization up into two parts, and you're going to see how much of it is in the direction of the applied external field and how much of it is perpendicular to the direction of the external applied field. And the longitudinal magnetization is the amount of magnetization in the same direction as the applied external magnetic field. So this is 100% in the equilibrium condition, and it cannot be measured directly. Why is that? Because you might remember that we're applying a field of 1.5 Tesla, 3 Tesla. So that's a very, very strong field. The tiny amount of magnetization coming from all these protons is very small. It can't be measured with this massive magnetic field in the same direction. So an interesting thing to note is that the total magnetization behaves like a single magnet with spin angular momentum. So the total magnetization, that is the sum of all of these protons together, is going to behave like a spinning magnet. So the proton itself is a tiny spinning magnet. It's also the effect of all these protons together in the external magnetic field is going to be that of a big spinning magnet. So what we need to do is we have to measure how much magnetization is there in the longitudinal direction, because that's how we create the MRI image. But we can't measure it in the longitudinal direction. We can only measure it in the transverse direction. What do we mean by transverse direction? We mean the direction which is perpendicular to the longitudinal direction. So perpendicular means 90 degrees. We can measure magnetization in the transverse plane. So what we need to do is tip over the longitudinal magnetization to measure it. The longitudinal magnetization is like this. We need to make all of it like this to measure it. So we already know that applying a field can change the alignment of a magnet. So what we do is we apply an oscillating magnetic field in the B1 in the transverse plane. Now imagine that all the protons together are like one spinning magnet. Now we're going to apply an oscillating magnetic field perpendicular to the field that's already applied. We know what happens when an oscillating magnetic field is applied. The magnet begins to precess. So what happens is the magnetization gets pushed and pulled like this, and it keeps going in the direction of the applied oscillating field until it's finally oscillating completely in the transverse direction. Another condition that applies here is that this oscillating field that's applied must have frequency equal to the Llama frequency. And for a field of 1.5 Tesla, this oscillating field lies in the radio frequency region. So a radio frequency pulse is applied at 90 degrees to the external magnetic field, This radio frequency pulse is called a 90 degrees radio frequency pulse. The radio frequency pulse pushes and pulls the magnetization. The magnetization behaves like a magnet would spin. Once it's pulled a little, it precesses at a new angle. So first it's completely pointing upward in the direction of the magnetic field. You apply a radio frequency pulse, which has the Llama frequency to it. Now what's going to happen is the thing is going to start flipping, it's going to start precessing. So it goes a little lower and it starts precessing. Then it gets pulled a little more, so it goes a little lower and starts precessing, until finally it's completely lying 90 degrees to the external applied field, the big field we're applying, and it's precessing around B0 at 90 degrees. So in this way, B1 pulls and pushes the magnetization, magnetization M spirals down until it is precessing in the transverse or the XY plane. So immediately after the radio frequency pulse, the longitudinal magnetization is 0% and the transverse magnetization is 100%, and all the individual spins are in phase. What does in phase mean? They're all spinning in the same time. So they all add to each other instead of subtracting from each other. Okay, so I have a question for everybody. Before the RF pulse, what is the percentage of longitudinal magnetization and what is the percentage of transverse magnetization? Before the RF pulse. So that's the question. Can you put the answers in the chat box? So we're saying that after the RF pulse, the longitudinal magnetization is 0%. And the transverse magnetization is 100%. So before the RF pulse, what is the longitudinal magnetization and what is the transverse magnetization? That's the question. Can anybody answer that? Okay, I'm not sure if you're giving answers. Wait, let me try creating a question and answer. Oh no, there's no questions that have been asked yet. Okay, I'm not sure if I'm not seeing your answers, but all right. I'll give you the answer myself. The longitudinal magnetization is 100% and the transverse magnetization is 0% before the RF pulse is applied. And afterwards, the longitudinal magnetization is 0% and the transverse magnetization is 100%. So yeah. Okay. What happens post excitation? Excitation means we apply the RF pulse, the magnetization gets tipped over and it's precessing in the transverse plane. So now we're not going to talk about the big magnetization anymore. We're going to talk about the individual spins again. Now, the spins which were all spinning at the same time start to lose their synchronicity and start to dephase. And this happens because each little spin creates a magnetic field of its own that interacts with the neighboring spin. And also because even though we're trying to apply a perfectly uniform magnetic field, there's imperfections in the field. So one spin is in a region of slightly higher magnetic field. One spin is in a region of slightly lower magnetic field. And as a result, they're going to start spinning at different times. This means that they become out of phase. They begin to dephase. Now, the transverse magnetization is the sum of the total number of spins. When the spins begin to dephase, the transverse magnetization decreases. Eventually, the net transverse magnetization is 0 because the spins of all the protons have dephased completely. So this is what the transverse pulse looks like. After the 90-degree RF pulse has stopped, phase coherence goes down, transverse magnetization goes down, and the induced receiver coil voltage also goes down. So we have the free induction decay signal on the left-hand side. So you can see that initially the signal that we're getting from the transverse magnetization is high. But then after that it decreases, and finally it's almost 0. Yeah, so this is explaining the spin-spin interaction. So every spin has a field. Each spin is a magnet. Local differences in field exist. The Llama frequency of individual spins change, spins dephase, and transverse magnetization decreases. So this is explaining how transverse magnetization decreases. Now, the constant describing the mono-exponential decrease of the envelope is called the T2 or the spin-spin relaxation time. I'll explain what that means in just a second. Are we following till now? So what's happening is we talked about how these spinning magnets behave. We talked about the Llama frequency. We said when we apply an external oscillating magnetic field, they'll gain energy and then they'll lose it, and then we'll get a signal. We talked about longitudinal magnetization and we talked about transverse magnetization. Longitudinal magnetization is in the direction of the applied external field, and transverse magnetization is at right angles to it. We said why we can't measure longitude magnetization directly, because there's another very strong field in the same direction. So we talked about, all these protons are spinning, precessing at a certain angle to the B naught, and they are acting like a big magnet would spin. So we know how to tip over spinning magnets. We just have to apply an oscillating field to them. So what we did is we applied an oscillating field at 90 degrees. This oscillating field pushes and pulls the magnet until it's spinning in the 90 degrees direction. And at this point, the transverse magnetization is 100%. Now, what happens is the spins interact with each other. The neighboring spins have a magnetic field. The magnetic field itself has imperfections. Their Llama frequencies begin to change and the spins begin to dephase. Now, when the spins dephase, the total magnetization in the 90 degrees direction becomes zero, because for every spin which is in one, which is like +1, there's another spin which is -1. Or if the spin is +2, there's another spin which is -2. All the spins have dephased and they all cancel each other out, and the transverse magnetization is zero. So what we're able to measure is the transverse magnetization. And the transverse magnetization causes an induced receiver coil voltage. And it's that voltage, which is known as the free induction decay signal, that we're measuring on the left-hand side. So you can see that it starts off very high and then it goes to zero. Yeah. So how do we describe this way in which it goes to zero in such a way that we get an image out of all of this? We're getting there. So if you draw an envelope around those curvy lines, you get a mono-exponential decrease. Now, mono-exponential decreases can be described with the use of a single time constant. And it's that time constant which is known as T2, or the spin-spin relaxation time. And it is this T2 that we will measure and show on the image. So we'll say this tissue has a particular T2, this lesion has a particular T2, this bone has a particular T2. So it depends on how quickly the spins dephase. That's what describes, this is the T2 curve. So we have a number which describes the curve, and that number is what we show on the image. The shape of the T2 curve depends on molecule size, molecule packing, amount of water, and temperature, because it's the magnetic fields which are around which interacts with it. Now, FID actually falls to zero quicker than expected. This is because the spins precess differently depending on position and imperfect B naught field. So you can see that T2 decay and T2 star decay are two different things. So T2 star takes into account spin-spin interactions and main field inhomogeneities, and it gives us a different curve. Essentially, if we assume that the field is perfect, we would assume that the spins would dephase in a certain time, but in reality, they dephase in a much different time. So there's a difference between these two, which is known as T2 and T2 star. T2 star is a steeper curve, it goes to zero quicker, so it has a higher time constant. Okay, so we're 50 minutes into the webinar at this point. So I will not go into the spin echo sequence right now. We'll just say that the modern fields are perfect to 1 part and 2 into 10 to the power 7, but this is significant on the atomic scale, and this causes the difference between T2 and T2 star. So we'll go into the spin echo sequence, which is the difference between measuring T2 and T2 star, and we'll go into T1 relaxation in the next webinar. But now I'd like to give you a chance to ask any questions you have about the content we've shared. We've covered quite a bit. Let me just take you through what we've discussed in this webinar. So we talked about the advantages of MRI, and we talked about the disadvantages of MRI. We talked about the specific clinical parameters that we're able to image, which include T1, T2, and T2 star that we're discussing right now. We talked broadly about the setup of the MRI and how it works. We talked about the basics of protons and spin, etc. We talked about the setup. We talked about nuclear magnetic resonance. We talked about Llama frequency and Llama precession. We talked about magnetization, longitudinal and transverse. We talked about excitation. We talked about what happens post-excitation. We talked about spin-spin relaxation, which leads to the T2 curve. And we briefly discussed T2 star. And in the next webinar, we'll see more about T1, more sequences, localization of the signal, things like that. We'll see how this finally leads to an image. But yeah, since we're already 51 minutes in, I think we'll stop at this point. Are there any questions? Would you like to put any questions in the chat box? I hope this webinar has not left you more confused about MRI than when you started. I promise it'll all come together on the next webinar. So yeah, so please do attend that one as well. So I do have a message to send to everybody, which has the links that I'm supposed to send across. So just 1 second. Yeah, okay, so the link to join the FRCR Part 1 group, and that's this link. And the link to leave feedback for the webinar. Please do leave feedback because I go through the feedback very systematically. And if there's anything I could do to make the sessions more helpful, I would love to know so that I can do that. So those links are in the chat there. Oh, I can see somebody's used the link right now. That's really nice. If anybody could, if you could leave feedback, that would be really lovely. I would really appreciate that. All right, if there's no questions, then I think we can end the webinar at this point. I'll stop the recording. Thank you so much for joining in for the webinar. I hope you enjoyed it. How do I stop the recording?